This is an audio recording for visually impaired students from the book Pradeep's Organic Chemistry, Volume 1 by Dr. S.N. Dhawan. Alkyl and Aryl halides. Heading 9.1 Introduction. Compounds obtained by replacement of one or more hydrogen atoms of a hydrocarbon by an equal number of halogen atoms are called halogen derivatives of hydrocarbons. Many halogen containing organic compounds occur in nature and some of these are medicinally useful. For example, the chlorine containing antibiotic chloramcitin or chloramphenicol produced by soil microorganism is very effective for the treatment of typhoid fever. Our body produces an iodine containing hormone called thyroxine, the deficiency of which causes the disease goiter. Some synthetic halogen containing compounds are very useful in healthcare and medicine. For example, chloroquine is used for the treatment of malaria, fever, and halothane is an anesthetic agent used during surgery. Certain perfluorinated, that is, fully fluorinated compounds are thought to be potential blood substitutes in surgery. Many synthetic organic halogen compounds are extensively used in agriculture and industry and hence are being manufactured in large quantities every year. Organic halogen compounds serve as valuable intermediates for the synthesis of variety of other classes of organic compounds. Therefore, in this unit, we shall briefly discuss the preparation, properties and uses of simple organic halogen compounds. Heading 9.2 Classification of halogen compounds. The halogen derivatives of hydrocarbons are broadly classified into the following two types. First, aliphatic halogen compounds. These are obtained by replacement of one or more hydrogen atoms of an aliphatic hydrocarbon by an equal number of halogen atoms. Depending upon the nature of the aliphatic hydrocarbon, whether alkane, alkene or alkyne, aliphatic halogen compounds are of the following three types. A. Haloalkanes. The halogen derivatives of alkanes are called haloalkanes. These are classified as fluoro, chloro, bromo or iodo compounds according to the type of halogen present and as mono, di, tri, tetrahaloalkanes etc. according as the contain 1, 2, 3, 4 etc. halogen atoms respectively in their molecules. For example, some of them are methyl chloride, methylene chloride, chloroform, carbon tetrachloride. Note: wherever two names are given under the formula, the one outside the brackets refers to the IUPAC name, while that given within the brackets denotes the common or the trivial name. B. Haloalkenes or alkynyl halides are the halogen derivatives of alkenes. Their general formula is CnH2n-1x, where X is equal to fluorine, chlorine, bromine or iodine and N is equal to 2, 3, 4 etc. For example, vinyl chloride, allyl bromide, crotyl chloride, cinnamyl chloride. C. Haloalkenes or alkynyl halides are the halogen derivatives of alkynes. Their general formula is CnH2n-3x, where X is equal to fluorine, chlorine, bromine or iodine and N is equal to 2, 3, 4 etc. For example, chloroacetylene, propergyl bromide and 1-bromoprop-1-ine. Second, aromatic halogen compounds. These are obtained by replacement of one or more hydrogen atoms of an aromatic hydrocarbon by an equal number of halogen atoms. These have been further classified into the following two major categories. First is nuclear halogen derivatives. Halogen derivatives of aromatic hydrocarbons in which the halogen atom fluorine, chlorine, bromine or iodine is directly attached to an aromatic ring are called aryl halides. Their general formula is Ar2x, where Ar short name for aryl represent as phenyl, a substituted phenyl or any other aryl group such as naphthalene etc. Some example of aryl halides are chlorobenzene, 1-bromo 4-methylbenzene or para-bromotoluene and orthoiodotoluene. Second, side chain halogen derivatives. Halogen derivatives of aromatic hydrocarbons in which the halogen atom is linked to one of the carbon atoms of the side chain carrying the aryl group are called alkyl halides. For example, benzyl chloride, benzyl dichloride, benzotrichloride, and beta phenyl ethyl bromide. Section A, alkyl halides. The monohalogen derivatives of alkanes are called alkyl halides or monohaloalkanes or simply haloalkanes. Their general formula is R bonded to X, where R is any alkyl group and X is any halogen atom, that is fluorine, chlorine, bromine or iodine. They are also represented as CnH2n plus 1x, where n is equal to 1, 2, 3, etc. These are obtained by replacement of one hydrogen atom of an alkene with a suitable halogen atom. Thus, alkene gives in the presence of X gives out RH, which is haloalkane or alkyl halide. Some important examples of haloalkanes are methyl chloride, ethyl bromide, and N-propyl iodide. Next heading 9.3, Nomenclature of alkyl halides. In the common or trivial system, the monohaloalkane derivatives of alkanes are called alkyl halides. Their individual names are derived by naming the alkyl group followed by the name of the halogen as halide, that is fluoride, chloride, bromide or iodide. The complex name of any alkyl halide is always written as two separate words. In the IUPAC system, the monohaloalkane derivatives of alkanes are named as haloalkanes. Their individual names are derived by prefixing the word halo to the name of the longest state chain alkane. The numbering of the parent state chain alkane is always done in such a way that the carbon atom carrying the halogen atom gets the lowest possible number. The IUPAC name of any monohaloalkane derivative of alkene is always written as one word. The common and IUPAC names of some monohaloalkanes derivatives or monohalogen derivatives of alkanes are given below. Common name or trivial name methyl chloride, IUPAC name chloromethane, common name ethyl bromide, IUPAC name bromoethane, common name N-propyl iodide, IUPAC name 1-idopropane, common name isopropyl iodide, IUPAC name 2-idopropane, common name N-butyl chloride, IUPAC name 1-chlorobutane, common name secondary butyl chloride, IUPAC name 2-chlorobutane, common name isobutyl chloride, IUPAC name 1-chloro-2-methyl-propane, common name tert butyl chloride, IUPAC name 2-chloro-2-methyl-propane, common name N-pentyl chloride or N-amyl chloride, IUPAC name 1-chloropentane, common name isopentyl chloride or isoamyl chloride, IUPAC name 1-chloro-3-methyl-butane, common name tert pentyl chloride or tert amyl chloride, IUPAC name 2-chloro-2-methyl-butane, common name neopentyl chloride or neoamyl chloride, IUPAC name 1-chloro-2-2-dimethyl-propane. Next heading 9.4, Classification of alkyl halides. Classification of alkyl halides. Alkyl halides are further classified as primary 1 degree, secondary 2 degree and tertiary 3 degree according as the halogen atom is attached to primary, secondary and tertiary carbon atoms respectively. For example, primary alkyl halides, iodoethane or ethyl iodide. Next, 1-bromopropane or N-propyl bromide. Next, 1-chloro-2-methyl-propane or isobutyl chloride. Next, 1-bromo-2,2-dimethyl-propane or neopentyl bromide. Secondary alkyl halides, 2-chloropropane or secondary propyl or isopropyl chloride. Next, 2-bromobutane or secondary butyl bromide. Next, 3,3-dimethyl-2-bromobutane. Tertiary alkyl halides, 2-bromo-2-methyl-propane or tert butyl bromide. Next, 2-iodo-2-methyl-butane or tert pentyl iodide. Next heading 9.5 Methods of formation. Alkyl halides are usually prepared in the laboratory by the following general methods. First, from alcohols. The most convenient method for the preparation of haloalkenes involves the substitution of the OH group of an alcohol by the halogen atom. This can be done by the following methods. First, by the action of halogen acids. Alcohols are converted into haloalkenes by the action of halogen acids, in which alcohol plus HX in the presence of heat is converted into haloalkane plus H2O. For a given alcohol, the reactivity of the halogen acids in the above reaction follows the sequence Hi is the greatest, then HBr, and then HCl. And that of alcohols for a given halogen acid follows the order tertiary, the highest, then secondary, then primary. That is 3 degree, then 2 degree, and then 1 degree. Reason. This reaction is an example of a nucleophilic substitution reaction in which the nucleophile, that is halide ion, attacks the protonated alcohol molecule with the expulsion of water, a good living group. Since the nucleophilicity, that is tendency to donate an electron pair to the carbon atom of the halide ions, decreases in the order iodine negative, then Br negative, and then Cl negative, the order of reactivity of the halogen acids decreases in the same order, that is Hi, then HBr, and then HCl. Further, since the order of stability of the carbocations or the incipient carbocations in the transition state of these reactions follows the sequence 3 degree the highest, then 2 degree, and then 1 degree. The order of reactivity of the alcohols follows the same sequence, that is 3 degree alcohol, then 2 degree alcohol, and then 1 degree alcohol. Chloroalkenes or alkyl chlorides. Primary or secondary chloroalkanes or alkyl chlorides are prepared by passing hydrochloric acid gas through a suitable alcohol in the presence of anhydrous zinc chloride, which is Grove's process. Mechanism. The purpose of anhydrous ZnCl2 is to help in the cleavage of the CO bond. Being a Lewis acid, it coordinates with the oxygen atom of the alcohols. As a result, CO bond weakens and ultimately breaks to form carbocations. These carbocations then readily react with chloride ion to form chloroalkanes as shown below. If the nature of R positive is such that it can undergo rearrangement, the product will be rearranged alkyl halide. For example, neopentyl alcohol on heating with HCl does not give the expected neopentyl chloride but gives the rearranged alkyl halide, that is 2-chloro-2-methyl-butene as shown below. The driving force for this rearrangement is the greater stability of the 3 degree carbocation over 1 degree carbocation. If the concentration of ZnCl2 is low, the reaction is still catalyzed by acids but no rearrangement occurs. SN2 mechanism. Pyridine and dimethylamine can also catalyze the reaction between alcohols and hydrochloric acid without rearrangement. Tertiary alcohols, however, react readily with concentrated HCl even in the absence of zinc chloride. Bromoalkanes or alkyl bromides are obtained by refluxing a suitable alcohol with constant boiling hydrobromic acid 48% in presence of a little concentrated H2SO4 as catalyst. HBr can also be generated in situ during the reaction by the action of concentrated H2SO4 on KBr. Thus, iodoalkanes or alkyl iodides are prepared by refluxing a suitable alcohol with constant boiling hydric acid 57%. Hi may also be generated in C2 by the action of 95% phosphoric acid on Ki. Second, by the action of phosphorus halides. Phosphorus halides react with alcohols to form haloalkanes or alkyl halides in excellent yields 80% or above. Chloroalkanes or alkyl chlorides are prepared by the action of either phosphorus pentachloride PCl5 or phosphorus trichloride PCl3 on suitable alcohols. Alcohol plus phosphorus pentachloride gives out chloroalkane or alkyl chloride plus phosphorus oxychloride plus HCl, and there are some more examples for it. Similarly, bromoalkanes or alkyl bromides and iodoalkanes or alkyl iodides are prepared by the action of phosphorus tribromide PBr3 and phosphorus triiodide PI3 respectively on suitable alcohols. Since PBr3 and PI3 are not very stable compounds, these are generally prepared in situ by the action of red phosphorus on bromine and iodine respectively. Third, by the action of thionyl chloride. Chloroalkanes or alkyl chlorides are conveniently prepared by refluxing alcohols with thionyl chloride in presence of pyridine, that is C5H5N. Alcohol plus thionyl chloride in the presence of pyridine gives out chloroalkane plus SO2 and HCl. Thionyl chloride method is preferred over hydrogen chloride or phosphorus pentachloride method for the preparation of chloroalkanes, since both the byproducts SO2 and HCl in this reaction, being gaseous, escape, leaving behind the chloroalkanes in almost pure state. Second, from hydrocarbons. Alcohols can be prepared from alkenes and alkenes as discussed below. A. From alkenes. Alkenes react with halogen acids to form haloalkanes, the order of reactivity being Hi the highest, then HBr, then HCl, and then HF. The addition of hydrogen halides to an unsymmetrical alkene takes place according to Markovnikov's rule. The rule states that during the addition of unsymmetrical rearrangement, HX, H2O, H2SO4, etc., to unsymmetrical alkenes, the negative part of the adding reagent, addendum, that is, molecule to be added, goes to the carbon atom of the double bond which has lesser number of hydrogen atoms. However, in the presence of peroxides such as benzoyl peroxide, the addition of HBr but not of HCl or Hi to unsymmetrical alkenes take place contrary to Markovnikov's rule. This is known as peroxide effect or Karsich effect. B. From alkenes. Halogenation of alkenes with Cl2 or Br2 in presence of heat or light usually gives a complex mixture of mono, di, and polyhaloalkenes. For example, chlorination of methane gives four products, that is, methane in the presence of chlorine HNu or 520 to 670 Kelvin gives out CH3Cl chloromethane plus CH2Cl2 dichloromethane plus CHCl3 dichloromethane plus CCl4 tetrachloromethane. Although substitution beyond monohalogenation can largely be suppressed by controlling the ratio of halogen to alkane, yet this method is not much practical use in the laboratory, since the boiling points of these haloalkanes are quite close and hence cannot be easily separated. However, in industry, such complex mixtures can be easily separated using long fractionating columns. In case of higher alkanes, even monohalogenation gives a mixture of all the possible isomeric haloalkanes, indicating thereby that all types of hydrogens, whether 1 degree, 2 degree, or 3 degree, are substituted by the halogen atom. For example, propane in the presence of Cl2 HNu and 298 Kelvin gives out 1 chloropropane 45% plus 2 chloropropane 55%, and butane in the presence of Cl2 HNu 298 Kelvin gives out 1 chlorobutane 28% plus 2 chlorobutane 72%. The relative amounts of these isomeric haloalkanes, however, depend upon the nature of halogen Cl2 or Br2 and the number of type of hydrogen 1 degree, 2 degree, or 3 degree being substituted. In general, the ease of substitution of various hydrogens follows the sequence 3 degree the highest, then 2 degree, then 1 degree, but their relative rates vary with the nature of halogen. For example, with Cl2, the relative rate of substitution of 3 degree, 2 degree, and 1 degree hydrogens at 298 Kelvin is 5 ratio 3.8 ratio 1, while with Br2 it is 600 ratio 82 ratio 1 at 400 Kelvin. Iodination is reversible, but it may be carried out in the presence of an oxidizing agent such as HiO3, HNO3, HgO, etc., which destroys the Hi as it is formed and thus drives the reaction in the forward direction. Fluorination of hydrocarbons with pure F2 gas occurs explosively. This is partly due to low bond dissociation energy of F2 molecule 150.6 kJ per mole, and partly due to strongly exothermic nature of one of the termination steps, that is R free radical plus F free radical gives out Rf. This step is so exothermic, 447.7 kJ per mole, that the energy released is larger than the required to break a carbon-carbon bond, 347.3 kJ per mole, thereby resulting in fission of the molecule. However, direct fluorination of hydrocarbons may be carried out successfully by diluting F2 with an inert gas such as N2 or argon. Alternatively, alkyl fluorides are more conveniently prepared indirectly by heating suitable chloroalkanes with inorganic fluorides such as ASF3, SBF3, COF3, AgF, Hg2F2, etc. For example, bromomethane plus HgF gives out fluoromethane plus HgBr, and chloroethane plus Hg2F2 gives out fluoroethane plus Hg2Cl2. This reaction is called Schwarz reaction. When the organic halide contains 2 or 3 halogen atoms at the same carbon, COF3 or the more easily available SBF3 is used. For example, 2,2-dichloropropane plus 2-SBF3 gives out 2,2-difluoropropane plus 2-SbCl3. Third, by halide exchange. Iodoalkanes can be easily prepared from the corresponding chloroalkanes or bromoalkanes by heating with sodium iodide in acetone or methanol. Bromomethane plus NaI in the presence of acetone and heat gives out iodoethene plus NaBr. This reaction is called Finkelstein reaction and is based upon the fact that NaBr, being less soluble than NaI in acetone or methanol, gets deposited during the course of the reaction. As a result, the equilibrium shifts in the forward direction. Fourth, from silver salt of fatty acids. Bromoalkanes can be easily prepared by refluxing the silver salt of a fatty acid with bromine in carbon tetrachloride. Silver propanate plus Br2 in the presence of CCl4 reflux gives out bromoethane plus CO2 plus AgBr. This reaction is called bromidine-Huntsdecker reaction or simply Huntsdecker reaction. Huntsdecker reaction is believed to occur by a free radical mechanism. The yield of the alkyl halide is primary, the highest, then secondary, then tertiary. Chloroalkanes can also be prepared by this method by using Cl2 instead of Br2, but the yields are poor. With I2, silver salts give esters instead of iodoalkanes. 2RCOOHG plus I2 in the presence of CCl4 gives out RCOOR plus CO2 plus 2AgI. This is known as Birnbaum-Simonini reaction. Next heading 9.6. Physical properties of alkyl halides. Some important physical properties of alkyl halides are discussed below. First, physical state, color, odor, etc. Alkyl halides are colorless when pure, but bromides, particularly iodides, develop color when exposed to light. Methyl chloride, methyl bromide, ethyl chloride, and some chlorofluoromethanes and chlorofluoroethanes are gases at ambient temperatures. Other chloro-bromo-iodo compounds are either liquids or solids. Many volatile halogen compounds have a sweet smell. Second, melting points and boiling points. The molecular masses of alkyl halides are higher than those of parent alkanes. As a result, the melting points and boiling points of haloalkanes are several degrees higher than those of parent alkanes, mainly due to greater magnitude of van der Waals forces of attraction. Second, for the same alkyl group, the boiling points of alkyl halides decrease in the order Ri the highest, then Rbr, then Rcl, and then Rf. This is because with the increase in the size and mass of the halogen, the magnitude of the van der Waals force of attraction increases. Thus, compound CH3I have boiling point 315 Kelvin. CH3Br 277 Kelvin, CH3Cl 249 Kelvin, CH3F has 195 Kelvin, and CH4 have 111 Kelvin. Third, for the same halogen atom, the boiling points increase with increase in the size of the alkyl group. Haloalkane CH3Cl have boiling point 249 Kelvin. CH3CH2Cl have 285.5 Kelvin. And CH3CH2 whole twice Cl has 320 Kelvin. And that of CH3CH2 whole 3 Cl is 351.5 Kelvin. Fourth, for isomeric alkyl halides, the boiling points decrease with branching. This is due to the reason that the branching the surface area of the alkyl halide decreases, and hence the magnitude of the van der Waals forces of attraction decreases. Thus, haloalkane CH3CH2 whole 3 Cl have a boiling point of 351.5 Kelvin, and CH3 whole 2 CH2 Cl have 342 Kelvin, and CH3 CH2 CHCl CH3 have 341 Kelvin, and that of CH3 whole 3 C to Cl is 324 Kelvin. Fifth, generally the boiling points of chloro, bromo, and iodo compounds increase as the number of halogen atoms increases. For example, haloalkane CH3Cl have a boiling point of 249 Kelvin. CH2Cl2 have 313 Kelvin. CHCl3 have 334 Kelvin, and CCl4 have 350 Kelvin. Second, solubility. Even though alkyl halides dipole moment 2.05 to 2.15 diopter are polar molecules, still they are insoluble in water. This is due to the reason that they can neither form hydrogen bonds with water nor can they break the hydrogen bonds already existing between water molecules. However, they are quite soluble in organic solvents of low polarity such as petroleum, ether, benzene, ether chloroform, carbon tetrachloride, etc. Since the intermolecular forces in these halo compounds are similar to those in the above solvents. Third, density. Alkyl fluorides and chlorides are generally lighter than water, whereas alkyl bromides and iodides are heavier. Their relative densities follow the order Ri, the highest, then Rbr, and then Rcl. Among the alkyl halides, methyl iodide has the highest density. However, as the size of the alkyl group increases, the density of alkyl halides go on decreasing. Further, the density increases with increasing number and atomic mass of the halogen. CH2Cl2 has a density of 1.336 gram per ml, and CHCl3 of 1.489, and that of CCl4 is 1.595. Fourth, stability. Since the strength of the CX bond decreases in the order CF the highest, then CCl, and then CBr, and then Ci, therefore stability of the alkyl halides having the same alkyl group decreases in the same order. Alkyl fluorides, then alkyl chlorides, then alkyl bromides, and then alkyl iodides. That is why alkyl iodides on standing become violet or brown because of their decomposition in presence of light to give iodine. Further, because of higher stability and easy availability, the most commonly used solvents in industry are organic chlorides rather than bromides and iodides. Fifth, inflammability. Organic halogen compounds are less inflammable than the corresponding hydrocarbons. The inflammability, however, decreases with increasing halogen content. Since organic halogen compounds are good solvents for fats and oils and also do not catch fire easily, polychloro compounds such as tri and tetrachloroethylenes are widely used as solvents for dry cleaning. Carbon tetrachloride is used as a fire extinguisher under the name pyridine. Next, heading 9.7, chemical reactions on alkyl halides. Haloalkanes or alkyl halides are highly reactive compounds due to the presence of a polar carbon halogen bond in their molecules. They undergo a number of important reactions such as nucleophilic substitution, elimination, halogenation, formation of organometallic reagents such as Grignard reagent, etc. It is because of this reason that haloalkanes are considered to be one of the most valuable synthetic reagents in organic chemistry. Some of the important reactions of haloalkanes are discussed below. First, nucleophilic substitution reaction. The halogen atom in haloalkanes, alkyl halides, is more electronegative than the carbon atom attached to it. As a result, carbon atom acquires a partial positive charge and the halogen atom a partial negative charge. The presence of this small positive charge on the carbon atom makes it susceptible to attack by nucleophilic reagent, that is, reagents possessing a lone pair of electrons. Thus, when a nucleophile stronger than the halide ion approaches the positively charged carbon atom of an alkyl halide, the halogen atom with its bonding pair of electrons is displaced and a new bond between the carbon atom and the incoming nucleophile is formed. Such reactions in which a stronger nucleophile displaces a weaker nucleophile are called nucleophilic substitution reactions, and the atom or group halide ion in the present case, which departs with its bonding pair of electron, is called the leaving group. Better the leaving group, more facile is the nucleophilic substitution reaction. Amongst the halides ions, the order in which the leaving groups depart follows the sequence I negative, then Br negative, then Cl negative, and then F negative. It is because of this reason that the order of reactivity of haloalkanes follows the sequence iodoalkanes, then bromoalkanes, then chloroalkanes, and then fluoroalkanes. Relative reactivity of haloalkanes. As discussed above, the reactivity of haloalkanes is due to polarity of the carbon halogen CX bond. Obviously, at the first sight, it appears that greater the polarity of the CX bond, more reactive should be haloalkane. Now, polarity of the CX bond in methyl halides decrease in the order CH3Cl 1.94 diopter, the highest, then CH3F 1.82 diopter, then CH3Br 1.79 diopter, and then CH3I 1.64 diopter. Therefore, the reactivity of the haloalkane should also decrease in the same order, that is RCl, then RF, then RBr, and then RI. However, the actual order is Ri, then Rbr, then Rcl, and then Rf. This can be explained in terms of the bond association energy of the CX bond: 452, 351, 293, and 234 kilojoule per mole. Thus, Ci has the minimum bond association energy while Cf has the maximum. Therefore, Ci bond is the easiest to break and hence iodoalkanes are most reactive. Further, as the bond association energy increases, the ease of breaking the CX bond and the reactivity of the haloalkane decreases. Thus, the actual order is Ri, then Rbr, then Rcl, and then Rf. A few typical nucleophilic substitution reactions of haloalkanes are given below. First, substitution of halogen by hydroxyl group. Formation of alcohols. Haloalkanes on treatment with boiling aqueous alkalis or silver oxide in boiling water HgOH undergo hydrolysis to form alcohols. Substitution of halogen by alkoxy group. Formation of ethers. Haloalkanes, when treated with sodium or potassium alkoxides, form ethers or alkoxy alkanes. This reaction is called Williamson's synthesis. Ethers can also be formed by heating alkyl halides with dry silver oxide. Third, substitution of halogen by cyano group. Formation of alkyl cyanides or alkane nitriles. Haloalkanes or alkyl halides react with alcoholic solution of potassium cyanide to form alkyl cyanides or alkane nitriles as the major product along with a small amount of alkyl isocyanides. Alkyl cyanides are very useful compounds since they can be converted into first amides on partial hydrolysis with concentrated HCl or alkaline hydrogen peroxide, second carboxylic acids on complete hydrolysis with dilute mineral acids or alkalis, and third primary amines by reduction with nascent hydrogen obtained by the action of sodium on alcohol, Mendes reduction, or catalytically with H2 or Ni or with lithium aluminium hydride, that is LiAlH4. The reaction of alkyl halides with potassium cyanide gives us a convenient method for increasing the length of the carbon chain by one carbon atom at a time, that is, for ascending for the homologous series. Fourth, substitution of halogen by isocyanide group, formation of alkyl isocyanates. When the aqueous ethanoic solution of a haloalkene, particularly iodoalkane, is heated with silver cyanide, alkyl isocyanide or alkyl isonitrile or carbylamine is produced as the chief product along with a small amount of the corresponding alkyl cyanide. Alkyl isocyanates on the reduction gives secondary amines. Explanation. In the cyanide ion, both the carbon and nitrogen atom have a pair of electrons. Therefore, either the carbon or the nitrogen atom can act as the electron donor to the alkyl halide. Such nucleophiles which have more than one site through which the reaction can occur are called ambident nucleophiles. Thus, cyanide ion is an ambident nucleophile. Alkali metal cyanides like NaCN, KCN are predominantly ionic. In principle, the reaction can occur either through carbon or nitrogen, but in practice, the reaction occurs through carbon since carbon-carbon bonds are stronger than carbon-nitrogen bonds and hence alkyl cyanides are the chief products. On the other hand, silver cyanide is predominantly covalent, therefore only nitrogen electron pair is available for bond formation. As a result, alkyl isocyanates are the chief products. Fifth, substitution of halogen by nitrite group. Formation of alkyl nitrites. Haloalkanes react with sodium or potassium nitrite to form alkyl nitrites. Sixth, substitution of halogen by nitro group. Formation of nitroalkene. When an aqueous ethanoic solution of a haloalkene is heated with silver nitrite, a nitroalkene is formed. Explanation. Nitrite ion, like cyanide ion, is an ambident nucleophile since it has two sites, oxygen and nitrogen, through which it can attack an alkyl halide, whereas attack through nitrogen gives nitro compounds, attack through oxygen gives nitrites. Alkali metal nitrites are ionic compounds and hence have a negative charge on one of the oxygen atoms. Nucleophilic attack through this negativity charged oxygen atom on the alkyl halides mainly gives alkyl nitrites. In contrast, silver nitrite is a covalent compound and hence does not have a negative charge on the oxygen atom. Instead, both the oxygen atoms and the nitrogen atom carry lone pair of electrons. Since nitrogen is less electronegative, therefore lone pair of electrons on the nitrogen atom are more easily available for bond formation. In other words, nucleophilic attack occurs through nitrogen and hence silver nitrite predominantly gives nitro compounds. Seventh, substitution of halogen by carboxylate group. Formation of esters. Haloalkanes form esters when heated with an ethanolic solution of silver salt of a fatty acid. Eighth, substitution of halogen by amino group. Formation of amines. Haloalkanes, when heated with an ethanolic solution of ammonia in a sealed tube at 373 Kelvin, form a mixture of primary, secondary and tertiary amines along with quaternary ammonium salts. This reaction is called Hofmann ammonolysis of alkyl halides. Ninth, substitution of halogen by hydrosulfide group. Formation of thioalcohols. Haloalkanes on heating with an aqueous ethanolic solution of sodium or potassium hydrosulfide form thioalcohols. 10th, substitution of halogen by mercaptide group. Formation of thioethers. A. By heating an alkyl halide with sodium or potassium mercaptide. B. By heating an alkyl halide with sodium or potassium sulfide. 11th, substitution of halogen by alkynyl group. Formation of higher alkynes. When treated with sodium alkynides, Haloalkanes form higher alkynes. Sodium alkanides are themselves prepared by the action of sodamide or sodium in liquid NH3 at 196 Kelvin on terminal alkynes. 12th, substitution of chlorine or bromine by iodine. Formation of alkyl iodides. Alkyl chlorides or bromides, when treated with sodium or potassium iodide in acetone, undergo halogen exchange to form alkyl iodides. This reaction is called Finkelstein reaction and is used for the preparation of alkyl iodides from alkyl bromides or chlorides. Second, elimination reaction. Dehydrohalogenation, formation of alkenes. When a haloalkene is heated with a concentrated alcoholic solution of potassium hydroxide, a molecule of hydrogen halide is eliminated and an alkene is formed. The hydrogen of the alkyl halide which is eliminated comes from a beta carbon, that is the carbon atom next to that which carries the halogen, and the halogen from the alpha carbon, that is the carbon atom which carries the halogen. Since in this reaction the hydrogen atom is lost from the beta carbon, therefore this reaction is classified as beta elimination reaction. Similarly, 1-chlorobutane on dehydrohalogenation gives but1-ene. However, if the structure of the alkyl halide is such that it can undergo elimination in two different ways due to the availability of different types of beta hydrogens, then the more highly substituted alkene, that is, having lesser number of hydrogen atoms on the doubly bonded carbon atoms, is the major product of dehydrohalogenation. This generalization is known as Saint-Jeff's rule. If the substituted alkene formed during dehydrohalogenation is capable of showing cis-trans isomerism, the trans alkene, being more stable, is always formed as the major product. Ease of dehydrohalogenation. In the light of Saint-Jeff's rule, any alkyl halide that gives a more stable, that is more highly substituted alkene, must undergo dehydrohalogenation faster than the one which give a less stable, that is less highly substituted alkene. Consider, for example, the dehydrohalogenation of chloroethane 1 degree, 2-chloropropane 2 degree, and 2-chloro-2-methylpropane 3 degree. Thus, the ease of dehydrohalogenation of these three alkyl halides increases as the number of beta hydrogens increases. In general, the ease of dehydrohalogenation of different alkyl halides having the same halogen decreases in the order tertiary 3 degree, then secondary 2 degree, and then primary 1 degree. And for the same alkyl group having different halogens decreases in the order Ri, then Rbr, and then RCl. Third, reaction with metals. Most of the organic chlorides, bromides, and iodides react with certain metals to form compounds containing carbon-metal bond. Such compounds are called organometallic compounds. Some important reactions of alkyl halides with metals are discussed below. A. Reaction with magnesium. Formation of Grignard reagents. Haloalkanes react with magnesium turnings in dry ether to form alkyl magnesium halides, commonly known as Grignard reagent. Alkyl halide plus Mg in the presence of dry ether gives out Grignard reagent. As you will learn later, vinyl and aryl halides also form Grignard reagent. Grignard reagents are highly reactive compounds. They react with all compounds which can donate a proton to form hydrocarbons. Even water, alcohols, amines, terminal alkynes, etc. are sufficiently acidic to react with Grignard reagent to form the corresponding hydrocarbons. It is therefore necessary to protect Grignard reagent from moisture, otherwise these will react with water to form hydrocarbons. In other words, Grignard reagent provide us a good method for converting alkyl halides to hydrocarbons. Grignard reagents also react with O2 and CO2, therefore they should be prepared and used in the absence of air, preferably under inert atmosphere. Grignard reagents are very useful for preparation of different classes of organic compounds such as alcohols, aldehydes, ketones, carboxylic acids, etc. B. Reaction with sodium. Formation of higher alkenes. Alkyl halides react with metallic sodium in presence of dry ether to form symmetrical alkenes containing double the number of carbon atoms present in the alkyl halide. This reaction is called Wurtz reaction. This reaction generally fails with tertiary alkyl halides since under the basic conditions of the reaction they prefer to undergo dehydrohalogenation to form alkenes. When a mixture of two different alkyl halides is used, all the three possible alkanes are formed. That is why this is not good method for the preparation of unsymmetrical alkanes. C. Reaction with other active metals. Formation of organometallic compounds. Besides magnesium and sodium, alkyl halides also react with the other active metals such as lithium, zinc, mercury, lead, etc. in presence of dry ether to form the corresponding organometallic compounds. Tetraethyl lead TEL is used as an anti-knocking agent in gasoline used for running automobiles. Fourth, reduction. Formation of alkenes. Haloalkenes are reduced to the corresponding alkenes. This reduction can be done by any of the following reagent. First, hydrogen in the presence of a metal catalyst such as nickel or palladium or platinum. Second, hydrochloric acid in the presence of red phosphorus. Alkyl iodides can be reduced to the corresponding alkenes on reduction with Hi in presence of red phosphorus at 420 Kelvin. Third, reduction by dissolving metals such as Zn and CH3COOH or HCl, Zn and NaOH or ZnCu couple and alcohol etc. gives alkenes. Fourth, primary and secondary alkyl halides are readily reduced to alkenes by lithium aluminium hydride LiAlH4. Tertiary alkyl halides, however, undergo dehydrohalogenation to give alkenes. On the other hand, sodium borohydride NaBH4 reduces secondary and tertiary alkyl halides but not primary, whereas triphenyltin hydride PH3SNH reduces all the three types of alkyl halides. Fifth, halogenation. Alkyl halides on treatment with halogens in presence of light, heat or a catalyst give di, tri, tetra or polysubstituted alkenes. Sixth, isomerization. When a haloalkene is heated to 573 Kelvin or at a lower temperature in presence of a Lewis acid such as anhydrous aluminium chloride as catalyst, it undergoes isomerization in which the halogen moves from one position to the other while the carbon skeleton of the molecule remains the same. Next heading 9.8 Nucleophilic substitution reactions. We have seen above that the most important reactions of alkyl halides are nucleophilic substitution reactions. These are mainly of the following two types. First, SN2, nucleophilic substitution by molecular reactions. Second, SN1, nucleophilic substitution unimolecular reactions. First, SN2 reactions. If the rate determining step of a nucleophilic substitution reaction involves both the substrate alkyl halide and the nucleophile, the reaction is referred to as SN2. In other words, the rate of this reaction depends upon the concentration of both the alkyl halide as well as the nucleophile. That is, rate is directly proportional to alkyl halide into nucleophile. Thus, SN2 reactions show second order kinetics. Second, SN1 reactions. If the rate determining step of a nucleophilic substitution reaction involves only the substrate alkyl halide and not the nucleophile, the reaction is referred to as SN1. Evidently, the rate of these reactions depend only upon the concentration of the alkyl halide and is independent of the concentration of the nucleophile. That is, rate is directly proportional to alkyl halide. Thus, SN1 reactions show first order kinetics. Many SN1 reactions occur simply upon heating the alkyl halides in a pure solvent without adding any nucleophile. Such nucleophilic substitution reactions are called solvolysis reactions. In these reactions, the solvent serves both as the medium as well as the nucleophile and can greatly affect the rate of the reaction. Let us now discuss the mechanism and stereochemistry of these reactions with particular reference to alkyl halides. Heading 9.8.1 Mechanism and stereochemistry of bimolecular nucleophilic substitution SN2 reactions. A. Mechanism. The typical example of a SN2 reaction is the hydrolysis of methyl bromide with aqueous alcoholic sodium hydroxide, 80% ethanol and 20% water to produce methyl alcohol and sodium bromide. Kinetic studies reveal that the rate of this reaction depends upon the concentration of methyl bromide as well as hydroxide ions. In other words, the reaction shows second order kinetics. Thus, the reaction is concerted, that is, it occurs in one step through the intervention of a single transition state. For this reaction to occur, it is essential that the molecule of methyl bromide must collide with a hydroxide ion. Theoretically, the attack of the hydroxide ion can occur from any direction, but experimentally it has been demonstrated that the attack of the hydroxide ion actually occurs from the backside, that is, from the side opposite to the bromine atom as shown below. As the hydroxide ion approaches the methyl bromide molecule from the backside, it starts sharing its electrons with the carbon atom, and at the same time the bromine atom starts withdrawing its bonding electrons. In other words, the bond between carbon and oxygen of the hydroxide ion starts forming, and at the same time the bond between carbon and bromine starts breaking. Such a reaction therefore occurs through a transition state as shown above or in the figure 9.1. The transition state can be pictured as a structure in which the central carbon atom is sp2 hybridized and the three hydrogen atoms attached to it lie in a plane with mutual bond angle of 120 degrees. The OH group and the Br atom are partially bonded to each lobe of the p orbital, which is perpendicular to the plane of three hydrogen atoms. The carbon and OH bond is partially formed and the carbon and Br bond is partly broken. The hydroxide ion has a diminished negative charge since it has started sharing its electron with the carbon atom, and at the same time bromine develops a partial negative charge since it has started removing its bonding electrons. Such a picture of the transition state can be compared to a wheel and axle in which the three hydrogen atoms represent the spokes of the wheel and the HOC-Br bond as the axle. The potential energy profile for this reaction is shown in figure 9.2. The profile shows that there is only one transition state and no intermediates between the reactants and the products. The reactants are shown to be slightly higher in energy than the product since the reaction is exothermic. The transition state is a higher energy since the carbon atoms has 5 bonds, 3 full and 2 partial, and hence it lies at the top of the energy barrier separating the reactants from the products. Finally, as the transition state passes over to the products, the rehybridization of the carbon atom from sp2 or sp3 occurs and the groups or atoms attached to it change their relative positions. In other words, the configuration of the product relative to the reactant is inverted in much the same way as an umbrella turns inside out in a strong gale. Such an inversion of configuration is called Walden inversion and invariably occurs in SN2 reactions. B. Stereochemistry. We have discussed above that in SN2 reactions, the incoming nucleophile attacks the alkyl halide molecule from the backside. As a result, the configuration of the molecule is inverted. However, from the results of hydrolysis of an achiral alkyl halide such as methyl bromide, it is impossible to tell whether the inversion of configuration has occurred or not, since both the front side and back side attack of the hydroxide ion give the same product, that is methyl alcohol, which is achiral. However, by examining the hydrolysis of a chiral optically active alkyl halide, it is possible to demonstrate that SN2 reactions in fact occur with inversion of configuration. Let us consider the alkaline hydrolysis of 2-bromo-octane, which gives 2-octanol. Both 2-bromo-octane and 2-octanol are chiral molecules, and hence each one of them exists as a pair of enantiomers. Now it has been established by a series of chemical reactions that both 2-bromo-octane and 2-octanol have the same absolute configuration, that is R rectus. Similarly, 2-bromo-octane and plus 2-octanol have the same absolute configuration, that is S sinister. Now, when R negative 2-bromo-octane is hydrolyzed under SN2 condition, high concentrated of hydroxide ions, it gives exclusively S positive 2-octanol. Since we know that positive 2-octanol has opposite absolute configuration, that is S, as compared to that of negative 2-bromo-octane, that is R, it establishes without any doubt that during the displacement reaction, inversion of configuration has occurred. Similarly, hydrolysis of S positive 2-bromo-octane exclusively gives R negative 2-octanol. Further proof of inversion of configuration during SN2 reaction has been provided that Hughes and Ingold, they observed that when optically active 2-iodoctane was treated with NaI having radioactive iodine, there occurred exchange of radioactive iodine between 2-iodoctane and NaI. The reactions showed second order kinetics SN2 mechanism, first order each in 2-iodoctane and NaI. Further, it was observed that the iodine exchange was accompanied by loss of optical activity, and the rate of loss of optical activity was twice the rate of iodine exchange. In other words, when one molecule of 2-iodoctane exchanged iodine, its configuration was inverted, thereby producing an enantiomer which compensated the optical activity of the second molecule. This clearly shows that backside attack has occurred, since if iodide would have attacked from the front side, it would have passed through the transition state 1, leading to the formation of a product with retention of configuration, that is without any loss of optical activity. To account for these observations, it is certain that nucleophilic attack occurs from the backside, passes through the transition second, ultimately giving a product with inversion of configuration. Next, heading 9.8.3, factors affecting the reactivity of alkyl halides in SN2 reactions. The relative reactivity of alkyl halides in SN2 reactions depends upon the following factors. First, structure of the alkyl halide. Steric effects. We have seen above that the hydrolysis of CH3Br by aqueous NaOH occurs by SN2 mechanism, which involves the backside attack of the nucleophile OH negative on the carbon bearing the bromine atom. Evidently, as the 3 hydrogen atoms of CH3Br are successively replaced by bulkier alkyl groups, that is methyl, ethyl, etc., the crowding steric hindrance in the reactant as well as in the transition state should increase accordingly. Due to this crowding, the nucleophile finds it more and more difficult to attack the carbon bearing the halogen atom. In other words, due to steric hindrance to the attack of the nucleophile, the E active for the transition state should increase and the rate of SN2 displacement should decrease. This has actually been found to be so. The relative rates of SN2 displacement reactions of some common alkyl halides by iodide ion are given in table 9.1. Table 9.1, relative rates of SN2 reactions of some alkyl halides. Type methyl. Relative rate of SN2 displacement 150. Type 1 degree. Rate of SN2 displacement 1.0. And for 2 degree 0.008. For 3 degree 0.0001. And for 1 degree neopentyl 0.00001. Thus, it follows that, in general, the decreasing relative reactivity of alkyl halides in SN2 reaction follows the sequence: methyl halides the greatest, then primary 1 degree, then secondary 2 degree, then tertiary 3 degree, and last neopentyl halides. Second, strength or the nucleophilicity of the nucleophile. Since the transition state for an SN2 reaction involves the nucleophile, therefore, nucleophilicity of the nucleophile plays an important role in determining the rate of an SN2 reaction. The nucleophilicity of a reagent may be defined as its ability to donate a pair of electrons to the carbon atom. Thus, greater is the nucleophilicity of a nucleophile, the more rapid would be its SN2 reaction. The relative nucleophilicities of some important nucleophiles in SN2 reactions on methyl bromide follow the sequence HS, then ratio CN, ratio I negative, ratio CH2CH2O negative, ratio OH negative, ratio Br negative, ratio C6H5O negative, ratio Cl negative, then CH3 whole 3N, then CH3COO, and then F negative, and then H2O. Third, nature of leaving group. The nature of the leaving group greatly affects the rates of SN2 reaction. In most of these reactions, the leaving group departs with a negative charge. Thus, groups atoms which can best stabilize the negative charge are the best leaving groups. Evidently, better the leaving group, more rapid is the SN2 reaction. This may be explained as follows. In the transition state for SN2 reactions, the negative charge is normally distributed over the nucleophile and the leaving group. The better the leaving group, more stable is the transition state due to greater stabilization of the negative charge by the leaving group, and hence more rapid is the reaction. Now the question arises as how to decide whether a particular leaving group is good or poor. This may be done as follows. The stability of an anion is inversely proportional to its basicity. Therefore, best leaving group are weakest bases. Table 9.2 lists some common good and poor leaving groups along with their basicities and relative reactivity in SN2 reactions. From the above table, it follows that 2-silate ion is the best leaving group through its basicity is slightly higher than that of bromide and iodide ions. Iodide and bromide ions are excellent leaving groups. Chloride ion is poor and fluoride ion is the poorest leaving group among halogens. Fourth, polarity of the solvent. Solvents play an important role in the rates of SN2 reactions. The most common SN2 reaction involves the interaction of an anion nucleophile with a neutral molecule. In the reactants, the negative charge is concentrated on the nucleophile, but in transition state, the negative charge is dispersed over OH group and X atom. Thus, the transition state is less polar than the reactants. Evidently, polar protic hydroxylic solvents such as water, alcohols, etc. should stabilize the reactants more effectively than the transition state and hence should slow down the SN2 reaction. Although a number of solvents have been used in SN2 reactions, but methanol and ethanol are preferred because they are inexpensive and easily removed after the reaction. However, the rates of many SN2 reactions are slow in protic hydroxylic solvents, primarily because the protic solvents greatly decrease the reactivity of most electrophiles by hydrogen bonding. A negatively charged nucleophile that is surrounding by a case of solvent molecules is more stabilized and therefore less reactive than bare or naked nucleophile. Therefore, to increase the rate of sluggish SN2 reaction, polar aprotic non-hydroxylic solvents such as acetonitrile CH3CN, dimethyl formamide CH3 NCHO, dimethyl sulfoxide CH3 SO, and hexamethyl phosphoramide CH3 N thrice PO are commonly used. Although these solvents can dissolve many salts because of high dielectric constant, but they do not solvate nucleophiles strongly. Free nucleophiles therefore have a far greater effective nucleophilicity in these solvents and hence SN2 reaction take place at faster rates. In terms of energy profile diagram, the effect of polar aprotic solvents on SN2 reaction is to lower the free energy of activation by destabilizing, raising the ground state energy level of the nucleophile. Next heading 9.5.4 Mechanism and Stereochemistry of Unimolecular Nucleophilic Substitution SN1 Reactions. Mechanism. The typical example of an SN1 reaction is the hydrolysis of tert butyl bromide with hydroxide ion. Kinetic studies reveal that the rate of this reaction depends only upon the concentration of tert butyl bromide and is independent of the concentration of hydroxide ions even though they are consumed in the reaction. Rate is directly proportional to CH3 whole thrice CBr. This rate law suggests that the reaction occurs in two steps. A. The first step involves the ionization of tert butyl bromide to produce tert butyl carbocation and the bromide ion. This step is slow and hence is the rate determining step of the reaction. B. The second step involves the attack of the nucleophile OH negative ion on the carbocation to produce tert butyl alcohol. This step is fast and hence does not affect the rate of the reaction. The potential energy profile of an SN1 reaction clearly shows that the reaction occurs through two transition states with carbocation as the intermediate. The first step involving the ionization of an alkyl halide to form the carbocation intermediate is highly endothermic and hence the transition state corresponding to this step has a high energy. It is because of this high energy transition state that makes the first step as the rate determining step of a SN1 reaction. The second step involving the attack of the nucleophile on the carbocation intermediate is highly exothermic and hence the transition state corresponding to this step has low E. Due to this low energy transition state, the nucleophile attacks the carbocation almost as soon as it is formed. This explains why the strength or the concentration of the nucleophile does not affect the rate of an SN1 reaction. B. Stereochemistry. We have discussed above that SN1 reaction occur through carbocation intermediates. A carbocation is a planar chemical species in which the positively charged carbon is sp2 hybridized. The three substituents attached to it lie in a plane 120 degree apart with an empty p orbital perpendicular to the plane. Now if the carbocation is formed from a chiral alkyl halide, the attack of the nucleophile on this carbocation is either lobe at the empty p orbital can occur with equal probability. Attack from the front side gives a product with retention of configuration, that is, the nucleophile occupies the same position in the product as the leaving group did in the reactant. However, if the attack of the nucleophile occurs from the back side, a product with inversion of configuration is obtained. This implies that the SN1 reaction on optically active halides should give a racemic mixture. However, complete racemization is usually not observed in SN1 reaction. What is actually observed is racemization with some inversion, that is, inversion product exceeds the retention product. This may be explained as follows. The initial ionization does not give a free carbocation. Instead of ion pair is first formed, in which the departing halide ion has not completely left the neighborhood of the carbocation. This ion pair may subsequently dissociate into a free carbocation depending upon its stability, that is lifetime. Now two possibilities arise. First, if the attack of the nucleophile is fast, it presumably occurs on the ion pair, but the departing halide ion almost shield the front side of the carbocation in the ion pair from nucleophile attack. As a result, backside attack is preferred and a product with inversion of configuration is obtained. Second, if the nucleophilic attack is slow, then the ion pair has sufficient time to dissociate into the corresponding free carbocation. The nucleophilic attack on the free carbocation can then occur with equal ease both from the front side and back side, giving a racemic mixture of the product. The overall result of these two reactions is that product is only partially racemized. For example, when R-2-bromooctane or S-2-bromooctane is hydrolyzed under conditions low concentration of HO- ions which favor SN1 reaction, only a partially racemized 2-octanol is formed as depicted. From the above discussion, it is clear that the extent of racemization depends upon stability, that is lifetime of the carbocation. The more stable carbocation gives more racemization product, while the less stable carbocation gives a product with net inversion of configuration. Evidence for carbocation intermediates. An elegant proof in favor of carbocation intermediates is SN1 reaction is provided by substitution reaction of benzyl chloride, which forms an unusually stable carbocation. When this compound is treated with tetramethyl ammonium fluoride in liquid SO2, it undergoes substitution to form benzyl hydryl fluoride. The rate of this reaction depends upon the concentration of benzyl chloride and is independent of that of fluoride ion. As the reaction proceeds, the rate of reaction gradually decreases. Alternatively, the rate of the reaction can also be slowed down by addition of chloride ions from outside. These observations can be explained if we assume that a carbocation is formed as an intermediate in the rate determining step of this reaction. In principle, this carbocation can be attacked either by fluoride or chloride ion with equal ease. As the concentration of the chloride ion increases either by gradual ionization of benzyl hydryl chloride or by adding a chloride salt from outside, they start competing with the fluoride ion of benzahydryl chloride, or by adding a chloride salt from outside, they start competing with the fluoride ion. As a result, starting material gets regenerated and the rate of the reaction falls. It may be noted here that such a retardation in rate is not observed if an unstable carbocation were the intermediate, because such carbocations have no time to wait for the departing ion, usually present in small concentration, to react again to form the starting alkyl halide. Next, heading 9.8.5, rearrangements in SN1 reactions. We have postulated above that carbocations are the intermediates in SN1 reactions. If this is so, then the initially formed carbocation should undergo rearrangement to the more stable carbocation, provided the structure permits, and the rearranged substitution product should be obtained. This has actually been found to be so. For example, when neopentyl bromide is boiled with ethanol, only the rearranged substitution product along with a small amount of an alkene elimination product derived from the rearranged carbocation is formed. These rearrangements are so common in SN1 reactions that in the absence of any other information, these are taken as a proof of SN1 reactions. However, no such rearrangements are observed in SN2 reactions, since the carbocations are not the intermediates and the one-step mechanism does not allow any opportunity for the rearrangement to occur. Solvolysis reaction. Nucleophilic substitution reaction in which the solvent also attacks as the nucleophile are called solvolysis reactions. These reactions occur by SN1 mechanism and are accompanied by rearrangement if the structure of the alkyl halide permits, as explained above in the reaction of neopentyl bromide with ethanol. If, however, the alkyl halide is optically active, then racemization occurs during solvolysis. Next, heading 9.8.6, factors affecting the rate of SN1 reactions. The following factors affect the rate of SN1 reactions. First, structure of the alkyl halide. We have discussed above that the carbocations are the intermediates in SN1 reactions. Therefore, the more stable the carbocation formed, the more rapid should be the SN1 reaction, but the relative stability of the carbocation follows the sequence benzyl allyl, then tertiary, then secondary, then primary, and then methyl carbocation. Therefore, the order of reactivity of alkyl halides in SN1 reaction follows the same sequence benzyl allyl, then tertiary, then secondary, then primary, and then methyl halides. However, it may noted here that this order of reactivity of alkyl halides is opposite to that for the SN2 reaction. Second, nature of the leaving group. In an SN1 reaction, the carbocation intermediate is formed by the removal of the leaving group. Evidently, better the leaving group, lesser is the E for the transition state leading to the formation of the carbocation, and hence more should be the reactivity of the alkyl halide in SN1 reaction. But the order of reactivity of the different leaving groups follows the sequence 2-silate ion, then I negative, then Br negative, then Cl negative, and then F negative. Therefore, the order of reactivity of the different substrates in SN1 reaction follows the same sequence. Alkyl 2 silates, then alkyl iodides, then alkyl bromides, then alkyl chlorides, and then alkyl fluorides. It may be emphasized here that this order of reactivity is the same as in SN2 reaction. Third, polarity of the solvent. The rate determining step of the SN1 reaction involves the formation of the ions, that is carbocation and the halide 2 or 2-silate ion. Therefore, polar protic solvents like water, alcohols, acids, etc. would solvate these ions. The solvation stabilizes the ions as well as the transition state leading to their formation. Further, the solvation process liberates a considerable amount of energy which facilitates the ionization step further. Thus, SN1 reactions are favored by polar protic solvents. Further, greater the polarity of the solvent, more is its ionizing power, and hence faster is the rate of SN1 reaction. The ionizing power of a solvent is determined by its dielectric constant. Higher the dielectric constant, greater is the ionizing power. Dielectric constant of some solvents are given below. Solvent CH3COOH, dielectric constant 6.2. CH3COH 10.9. CH3CH2OH 24.3. CH3OH 33.6. HCOOH 58. H2O 81. The solvent sometimes plays such a dominant role that it completely alters the mechanistic course of the reaction. For example, methyl bromide, which generally hydrolyzes in aqueous alcoholic medium by SN2 mechanism, can be made to hydrolyze by SN1 mechanism in formic acid containing small amount of water. Fourth, strength of the nucleophile. In SN1 reaction, the nucleophile does not take part in the rate determining step of the reaction. Therefore, the strength of the nucleophile has no effect on the rate of the reaction. Some important points of difference between SN1 and SN2 reaction are summarized on the next page. SN1 mechanism. First order kinetics. SN2 mechanism. Second order kinetics. SN1 mechanism, two-step reaction. SN2 mechanism, one-step reaction. SN1 mechanism, carbocations are intermediates. SN2 mechanism, carbocations are not intermediates. The reaction occurs through a transition state. SN1 mechanism, both black side and front side attack of the nucleophile occurs through the back side and attack predominates. SN2 mechanism, exclusive backside attack of the nucleophile takes place. SN1 mechanism, generally in racemization with some inversion, that is partial racemization is observed. SN2 mechanism, complete inversion of configuration occurs. SN1 mechanism, rearrangement are generally observed. SN2 mechanism, rearrangement are not observed. SN1 mechanism, elimination is an important side reaction. SN2 mechanism, elimination is not an important side reaction. SN1 mechanism, electronic factors affect the reaction rates greatly. SN2 mechanism, steric and not electronic factors affect the rates of the reactions. SN1 mechanism, the order of reactivity follows the sequence 3 degree, then 2 degree, then 1 degree, and then methyl halides. The order of reactivity follows the sequence methyl the highest, then 1 degree, then 2 degree, and then 3 degree alkyl halides. SN1 mechanism, weak nucleophiles such as water, alcohols, etc. favor these reactions. SN2 mechanism, strong nucleophiles such as alkoxide ions favor these reactions. SN1 reaction, low concentration of the nucleophiles generally favor them. SN2 mechanism, high concentration of the nucleophiles favor them. SN1 mechanism, polar protic solvents, water, alcohols, acids of the high dielectric constant favor SN1 reactions. SN2 mechanism, polar aprotic solvents, acetone, acetonitrile, dimethyl formamide, dimethyl sulfoxide, etc. of high dielectric constant favor SN2 reactions. However, methanol and ethanol are usually used since they are inexpensive and can be easily removed after the reaction. Next heading 9.9, polyhalogen compounds. Carbon compounds containing more than one halogen atom per molecule are called polyhalogen compounds. These are classified as di, tri, tetra, etc. halogen derivative according as they contain 2, 3, 4, etc. halogen atom per molecule. Many polyhalogen compounds such as chloroform and carbon tetrachloride are commercially useful compounds. Heading 9.9.1 Trichloromethane chloroform CHCl preparation. First, by distilling ethanol, ethyl alcohol, or propanol, acetone with a suspension of bleaching powder in water, laboratory method. The reaction in case of ethyl alcohol is supposed to take place as under. First, bleaching powder supplies both chlorine and calcium hydroxide. Second, chlorine acts both as an oxidizing as well as chlorinating agent. Third, chloral is then hydrolyzed by calcium hydroxide to give chloroform. In case of acetone, the reactions are CaOCl2 plus H2O gives out Cl2 plus CaOH whole twice. Acetone plus 3Cl2 in the presence of CaOH whole twice gives out 1,1,1 trichloropropane plus 3HCl. Acetone is preferred to ethyl alcohol as the yield is better. In place of bleaching powder, we may use in the laboratory an alkaline solution of sodium hypochlorite NaOCl obtained by the action of chlorine on cold sodium hydroxide solution. The various reactions taking place are as follows. Second, chlorination of methane. Industrial method. It is manufactured by chlorination of methane. The mixture so formed is separated by fractional distillation. Third, reduction of carbon tetrachloride. Industrial method. Reduction is brought about with iron fillings and steam. Fourth, pure chloroform can be prepared by the action of sodium hydroxide solution on chloral hydrate. Physical properties. Chloroform is a heavy colorless mobile liquid, boiling point 334 Kelvin, freezing point 210 Kelvin. It has sickly sweet smell and burning taste. It is sparingly soluble in water but readily dissolved in alcohol and ether. It is very good solvent for organic compounds. Inhalation of its vapor produces loss of conciseness and is therefore used in general and as aesthetic agent in surgery. Chemical properties. First, acidic nature. The hydrogen atom in CHCl3 is slightly acidic because of the following two reasons. First, due to I effect of the three chlorine atoms, the electron density in the CH bond is low. As a result, CH bond is weak and hence can be easily cleaved by a base. Second, the CCl3 negative ion left after the removal of a proton from CHCl3 is stabilized by resonance, in which Cl atom can expand its valence shell to a dissect because of the presence of d orbitals. This type of resonance is also called p-pi-d-pi electron delocalization or d orbital resonance. Second, oxidation. Oxidation. On exposure to air and sunlight, chloroform undergoes slow oxidation to form highly poisonous phosgene gas COCl2. So, to keep chloroform pure to be used as an anesthetic agent, first it is stored in brown bottles to cut off light. Second, the bottles are filled to brim to exclude any air. Third, 0.6 to 1% alcohol is added which destroys traces of phosgene that may be found on storage. Phosgene, thus formed, combines with ethyl alcohol to form non-toxic diethyl carbonate. Third, reduction. Reduction of chloroform with zinc and HCl gives methylene chloride. Reduction with zinc dust and water yields methane. Fourth, chlorination. When treated with chlorine in presence of sunlight, it is converted into carbon tetrachloride. Fifth, hydrolysis. On heating with concentrated aqueous or alcoholic potassium hydroxide, it is hydrolyzed to give potassium formate. Sixth, carbylamine reaction. Chloroform on warming with a suitable aromatic or aliphatic primary amine and alcoholic potash gives the corresponding isocyanide or the carbylamine, which has extremely unpleasant smell. Carbylamine reaction occurs through dichlorocarbene intermediate. This reaction is used as a test under the name carbylamine test or isocyanide test for both aliphatic and aromatic primary amines. Seventh, dehalogenation. Chloroform on warming with silver powder undergoes dehalogenation to give acetylene. Eighth, condensation with ketones. Chloroform adds to ketones in the presence of potassium hydroxide, for example, with acetone to give chloritone. Chloritone is used as an hypnotic sleep inducing drug. Ninth, nitration. Chloroform may be nitrated on heating with concentrated nitric acid to give chloropicrin or nitrochloroform. It is used as an insecticide. It has also been used as a war gas. 10th, Riemann-Tiemann reaction. Chloroform react with phenol and alcoholic KOH at 340 Kelvin to form salicylaldehyde as the major product. A small amount of para-hydroxybenzaldehyde is also obtained in this reaction. This reaction is called Riemann-Tiemann reaction and occurs through dichlorocarbene as intermediate. Uses: chloroform is used as first a solvent for resins, rubbers, oils and fats. Second, a preservative for anatomical specimens. Third, a laboratory reagent, example for testing primary amines. Fourth, in medicines. Fifth, it was once used as an anesthetic agent in surgery and as a flavoring agent in cough syrups, but because of its toxicity, it is no longer used for such purposes. Heading 9.9.2, tetrachloromethane carbon tetrachloride CCl4. Preparation: carbon tetrachloride is prepared industrially by the following methods. First, from methane. By chlorination of methane, natural gas in presence of partly reduced cupric chloride as catalyst. Second, from carbon disulfide. By chlorination of carbon disulfide in presence of ferric chloride or aluminium chloride as catalyst. Sulfur monochloride thus formed is separated by fractional distillation and then treated with fresh carbon disulfide to yield more carbon tetrachloride. Physical properties: it is colorless, volatile, non-inflammable liquid, boiling point 350 Kelvin. It has sickly smell. It is insoluble in water but dissolved readily in organic solvents such as alcohols, ether, etc. Chemical properties. Some important properties of carbon tetrachloride are given below. First, stability. CCl4 is stable to red heat about 773 Kelvin. Its vapors are highly non-inflammable, that is, do not catch fire. It is because of this property that CCl4 is used as a fire extinguisher under the name pyrene. At this high temperature, it is hydrolyzed by water to vapors to some event to form highly poisonous gas, that is phosgene. Second, reduction. On reduction with moist iron fillings, carbon tetrachloride gives chloroform. Therefore, after using it to extinguish fire, the room should be well ventilated. Third, hydrolysis. On boiling with alcoholic KOH solution, it undergoes hydrolysis to produce potassium carbonate. Fourth, reaction with antimony trifluoride. It reacts with antimony trifluoride in presence of antimony pentachloride as catalyst to form dichloromethane or furan. Furan is widely used as a refrigerant cooling agent in refrigerators and air conditioners. Fifth, Riemann-Tiemann reaction. Carbon tetrachloride reacts with phenol and alcoholic KOH at 340 Kelvin to form salicylic as the major product. A small amount of para-hydroxybenzoic acid is also formed in this reaction. Uses: carbon tetrachloride is used first as an industrial solvent for oils, fats, resins, liquors, etc., and also in dry cleaning. Second, as a fire extinguisher under the name pyrene. Third, for the industrial preparation of chloroform. Fourth, as a medicine for hookworms. Section B, aryl halides. As stated earlier in the unit, aromatic halogen compounds are of two types, aryl halides and alkyl halides. These two classes of compounds have widely different chemical reactivities, whereas aryl halides are far less reactive than alkyl halides. Alkyl halides are as reactive or even more reactive than alkyl halides. Heading 9.10, methods of preparation of aryl and alkyl halides. We have already discussed in this unit that haloalkanes can be easily prepared from alcohols by replacement of the OH group by the halogen atom. In contrast, Haloarenes or aryl halides cannot be prepared from phenols because it is difficult to replace the hydroxyl group of phenols by a halogen atom. This is due to the reason that because of resonance, the carbon oxygen bond in phenols has partial double bond character and is therefore stronger than carbon oxygen single bond in alcohols. Consequently, cleavage of carbon oxygen bond in phenols is difficult under ordinary conditions. Therefore, these are usually prepared by the following methods. First, from aromatic hydrocarbons by direct halogenation. A. Nuclear halogenation. Chloroarenes, aryl chlorides, and bromoarenes, aryl bromides, can be easily prepared by direct chlorination or bromination of aromatic hydrocarbons. The reaction is usually carried out at a low temperature 310 to 320 Kelvin in the absence of sunlight and in the presence of a Lewis acid such as anhydrous ferric or aluminium halide as catalyst. The function of the Lewis acid is to carry the halogen to the aromatic hydrocarbon. That is why these are usually referred to as halogen carriers. In addition to iron and aluminium halides, iodine and iron fillings have also been used as halogen carriers. Thus, chlorobenzene is formed when benzene is treated with chlorination in the presence of iron. Under the conditions of the reaction, iron first reacts with chlorine to form ferric chloride, which acts as a catalyst. For mechanism of halogenation, refer to Unit 8. If excess of halogen is used, a second halogen is introduced in the ring mainly at ortho and para positions with respect to the first since halogens or ortho-para directing. If toluene is used instead of benzene, a mixture of ortho and para chlorotoluenes is obtained since CH3 group is ortho-para directing. The ortho and para isomers can be easily separated due to large differences in the melting point. The direct iodination of aromatic hydrocarbons is not a useful reaction since the HI produced during the reaction, being a good reducing agent, reduces the aryl iodide back to the aromatic hydrocarbon and iodine. However, in the presence of oxidizing agents such as nitric acid, iodic acid, HiO3, mercuric acid, oxide, etc., the HI produced is either oxidized to iodine or is eliminated as mercuric acid iodide, and thus the reaction proceeds in the forward direction producing iodobenzene. Fluoroarenes, aryl fluorides, however, cannot be prepared by direct chlorination of aromatic hydrocarbons since the reaction is very violent and cannot be easily controlled. B. Side chain halogenation. The most convenient method for the preparation of side chain substituted aryl halides or alkyl halides is by the direct halogenation of suitable hydrocarbon. For example, when Cl2 is passed through boiling toluene in the presence of sunlight and the absence of halogen carrier, phenyl chloromethane benzyl chloride is formed. If Cl2 is passed for a longer time, the initially formed benzyl chloride reacts further to form first benzyl dichloride and then benzotrichloride. Instead of Cl2, sulfuryl chloride SO2Cl2 at 475 Kelvin in presence of light and traces of peroxide can also be used for side chain chlorination of arenes. When the side chain is larger than a methyl group, side chain halogenation preferentially occurs at the benzylic carbon, that is carbon atom next to benzene ring. That is why this is also called benzylic halogenation. Similarly, benzylic bromination can also be carried out with Br2 in presence of heat or light. A more specific reagent for benzylic bromination is, however, NBS, that is N-bromosuccinimide. Second, from aniline via diazonium salts. First, by Sandmeyer reaction. Chloroarenes, aryl chlorides, and bromoarenes, aryl bromides, are easily prepared when the diazonium salts are treated with CuCl dissolved in HCl or CuBr dissolved in HBr. This reaction is called Sandmeyer reaction. However, iodoarenes, aryl iodides, are prepared by simply warming the diazonium salt solution with aqueous Ki solution. For example, in Sandmeyer reaction, it is the halogen attached to copper which enters the benzene ring. Benzene diazonium chloride needed for the purpose is obtained by treating aniline dissolved in dilute HCl with an aqueous solution of sodium nitrite at 273 to 278 Kelvin, 0 degree to 5 degrees Celsius. Fluorines, aryl fluorides, are prepared by heating the corresponding diazonium tetrafluoroborates, which in turn are obtained by the diazotization of suitable aromatic primary amine with aqueous NaNO2 in presence of fluoroboric acid HbFO at 273-278 Kelvin. This reaction is called Ball-Schiemann reaction. Second, by Gutterman reaction. Haloarenes, particularly chloro and bromoarenes, can also be prepared by Gutterman reaction. It is modification of the Sandmeyer reaction. In this reaction, a mixture of freshly prepared copper powder in the presence of corresponding halogen acid HCl or HBr is used instead of cuprous halide dissolved in the corresponding halogen acid CuCl or HCl or CuBr HBr as used in Sandmeyer reaction. The yields are often around 40%. Third, by Hunt-Sticker reaction. When silver salt of an aromatic acid is heated with Br2 in CCl4, it undergoes bromination with simultaneous decarboxylation to yield aryl bromides. Heading 9.11 Physical properties of aryl halides. Some important physical properties of aryl halides are described below. First, melting points and boiling points. First, the melting and boiling points of haloarenes are nearly the same as those of haloalkanes with the same number of carbon atoms. Second, for the same aryl group, the melting and boiling points increases as the size of the halogen atom increases. That is, iodoarenes the highest, then bromoarenes, then chloroarenes, then fluoroarenes, and then arene. Thus, haloalkane or iodobenzene have 462 boiling pressure in Kelvin. Third, for the same halogen atom, the melting and boiling points increase as the size of the aryl group increases. Fourth, the boiling points of isomeric dihalobenzenes are nearly the same, but their melting points are quite different. Generally, the melting point of the para isomer is always higher than that of the ortho or the meta isomer. This is due to the reason that the para isomer is more symmetrical and hence its molecules pack closely in the crystal lattice. As a result, intermolecular forces of attraction are stronger and hence the para isomer melts at a higher temperature than the corresponding ortho and meta isomers. Second, solubility. Even though aryl halides mu is equal to 1.6 to 1.8 diopter are polar molecules, they are insoluble in water. This is due to the reason that aryl halides can neither form hydrogen bonds with water nor can they break the hydrogen bonds already existing between water molecules. However, they are quite soluble in organic solvents of low polarity such as petroleum, ether, benzene, ether, chloroform, carbon tetrachloride, etc. Since the intermolecular forces of attraction in these halocompounds are similar to those in the above solvents. Third, density. All aryl halides are heavier than water. Next, heading 9.12 Reasons for low reactivity of aryl and vinyl halides. Aryl halides and vinyl halides all contain a CX bond, but aryl halides and vinyl halides are far less reactive than haloalkanes towards nucleophilic substitution reaction. The following reason can be given to account for the low reactivity of aryl halides, taking chlorobenzene as an example. First, resonance effect. Chlorobenzene can be represented as a resonance hybrid of the following 5 structures. First, as a result, CCl bond acquires some double bond character, that is, chlorine is attached to carbon by little more than a single pair of electrons. On the other hand, in case of alkyl halides, say methyl chloride, carbon is attached to chlorine by a pure single bond. Consequently, carbon-chlorine bond in chlorobenzene is little stronger than in alkyl halides and hence cannot be easily broken. Like chlorobenzene, vinyl halides such as vinyl chloride can be represented as a resonance hybrid of the following structures. As a result, carbon-chlorine bond in vinyl chloride, like in chlorobenzene, is little stronger than in alkyl halides and hence cannot be easily broken. Second, as discussed above, aryl halides are stabilized by resonance but alkyl halides are not. Consequently, the energy of activation for the displacement of halogen from aryl halides is much greater than that of alkyl halides. Thus, aryl halides are much less reactive than alkyl halides towards nucleophilic substitution reactions. Second, hybridization of carbon bearing the halogen atom. An alternative explanation for the stronger carbon-chlorine bond in chlorobenzene or vinyl chloride as compared to methyl chloride can be offered on the basis of the type of hybridization of the carbon atom holding the chlorine atom. In methyl chloride, this carbon is sp3 hybridized, whereas in chlorobenzene or vinyl chloride, it is sp2 hybridized. Since sp2 hybridized orbitals is smaller in size as compared to sp3 orbital of carbon, therefore the carbon-chlorine bond in chlorobenzene or vinyl chloride should be shorter and hence stronger than in methyl chloride. This has been confirmed by the X-ray analysis, which shows that the carbon-chlorine bond in chlorobenzene is 1.69 Armstrong, whereas in methyl chloride it is 1.77 Armstrong. Third, polarity or nature of the carbon-halogen bond. Another reason for the low reactivity of aryl halides over alkyl halides is their lesser polar character. We know that a sp2 hybrid carbon is more electronegative than sp3 hybrid carbon. Therefore, the sp2 hybrid carbon of CX bond in aryl halides or vinyl halides is less willing to release electrons to the halogen than a sp3 hybrid carbon in alkyl halides. As a result, the carbon X bond in aryl halides or vinyl halides is less polar than in alkyl halides. This is supported by the observation that the dipole moment of chlorobenzene is just 1.7 diopter as compared to the dipole moment of methyl chloride that is 1.9 per diopter. Consequently, the halogen atom present in aryl halides cannot be easily displaced by nucleophiles. Next heading 9.13 Mechanism of nucleophilic aromatic substitution. The nucleophilic aromatic substitution can occur by the following two mechanisms. First, biomolecular displacement mechanism. Second, elimination addition or benzene mechanism. The bimolecular displacement mechanism involves relatively milder nucleophiles or bases and operates only in activated aryl halides containing electron withdrawing substituents at ortho and para positions with respect to the halogen atom. In contrast, addition, elimination or benzene mechanism involves relatively strong nucleophiles or bases and operates in unactivated aryl halides such as chlorobenzene and aryl halides containing electron donating groups at ortho and para positions with respect to the halogen atom. First, molecular displacement mechanism. According to this mechanism, the reaction proceeds in two steps. In the first step, the nucleophile attacks the carbon carrying the halogen to form an intermediate steps in carbon ion, which is stabilized by resonance. During the formation of the carbon ion, the hybridization of carbon involved changes from sp2 to sp3 and the aromatic character of the benzene ring is destroyed. This step therefore has a high energy and hence is the rate determining step of the reaction. In the second step, the intermediate carbon ion loses an halide ion to give the product in which the aromatic character is distorted. This step is fast and hence does not affect the overall rate of the reaction. The energy diagram for biomolecular nucleophilic aromatic substitution as shown in figure 9.7. Since in this mechanism, first step involves addition of a nucleophile and the second step involves elimination of halide ion, therefore this biomolecular mechanism is also called addition-elimination mechanism. Evidence in support. As stated above, the rate of the overall reaction largely depends upon the first step, that is formation of the carbon ion. This is supported by element effect. By element effect, we mean the effect of a particular element on the reactivity of a compound. In SN1 and SN2 reaction, the reactivity of alkyl halide follows the sequence: iodides the highest, then bromides, then chlorides, and then fluorides. In contrast, there is only a little difference in reactivity of aryl iodides, bromides, and chlorides. In nucleophilic aromatic substitution reaction, this suggests that the reactivity of various aryl halides is independent of the strength of the carbon-halogen bond. This can be explained only if the rate determining step of the reaction does not involve the cleavage of carbon-halogen bond. From the above discussion, it follows that the rate of biomolecular nucleophilic aromatic substitution is determined by the rate at which the nucleophile attacks the aromatic ring to form the intermediate carbon ion and not by the rate at which carbon-halogen bond breaks. Reactivity in nucleophilic aromatic substitution. We have discussed above that the rate of nucleophilic aromatic substitution depends upon the rate of formation of the carbon ion. Evidently, greater is the stability of the carbon ion, greater is the ease of the formation and hence more reactive is the aryl halide. Let us now compare the relative stabilities of carbon ions, first, second and third, resulting from nucleophilic attack of the OH negative on chlorobenzene, para-nitrochlorobenzene and para-chloroanisole respectively. The electron withdrawing NO2 group in carbon ion second tends to disperse the negative charge both by minus R and minus I effect. Therefore, carbon ion second is more stable than carbon ion 1. Aryl fluorides react much faster than chlorides, bromides, and iodides. This is probably due to the strong electron withdrawing inductive effect of the fluorine atom, which favors the initial nucleophilic attack on the aromatic ring. In other words, it stabilizes the transition state of the first step that will ultimately lead to its displacement. On the other hand, the electron donating OCH3 group in carbon ion third tends to intensify the negative charge relative to carbon ion first. As a result, carbon ion third is less stable than carbon ion 1. Thus, relative stabilities of the three carbon ions follows the sequence second the highest, then first, and then third. In other words, para-nitrochlorobenzene is more reactive than chlorobenzene, which in turn is more reactive than para-chloroanisole. In general, the presence of electron withdrawing groups increase the reactivity, while those of electron donating group decrease the reactivity of aryl halides towards nucleophilic aromatic substitution reactions. Let us now explain why the presence of electron withdrawing group at ortho and para position but not at meta position with respect to halogen activates the aryl halides towards nucleophilic aromatic substitution reaction. Consider for example, the carbon ions resulting from nucleophilic attack by the OH negative ion on ortho, para and meta chloronitrobenzenes. In case of ortho and para nitrochlorobenzene, one of the resonating structure IA in case of ortho isomer and second B in case of para isomer carries a negative charge on the carbon atom carrying the NO2 group. Therefore, these carbon ions are stabilized by resonance not only over the NO2 group but also on the benzene ring. However, in case of meta-nitrochlorobenzene, there is no such structure in which negative charge is present on the carbon atom carrying the NO2 group. Therefore, in case of meta-nitrochlorobenzene, the carbon ion is not stabilized by resonance over the NO2 group but is only stabilized by resonance over the benzene ring. In other words, carbon ion resulting from orthonitrochlorobenzene and para-nitrochlorobenzene are more stable than the resulting from meta-nitrochlorobenzene. Thus, presence of electron withdrawing group at ortho and para position but not meta with respect to the halogen activates the aryl halide towards nucleophilic aromatic substitution reaction. Further, greater the number of such groups at ortho and para position with respect to the halogen, more reactive is the aryl halide. It may be noted here that although the presence of NO2 group at meta position with respect to the halogen does not stabilize the resulting carbon ion by resonance effect, it does not stabilize it somewhat by the electron withdrawing inductive effect as compared to the carbon ion resulting from chlorobenzene itself. Consequently, meta-nitrobenzene is more reactive than chlorobenzene towards nucleophilic substitution reaction. Second, elimination addition or benzene mechanism. We have discussed above that electron withdrawing substituent at ortho and para position with respect to the halogen activate the aryl halides towards bimolecular nucleophilic substitution reactions. In the absence of such activating groups, aryl halides can still be made to undergo nucleophilic substitution reaction, but not only in the presence of strong nucleophiles such as NaNH2 in liquid NH3. For example, when chlorobenzene is treated with NaNH2 in liquid NH3 at 196 Kelvin, aniline is formed. Such nucleophilic substitution reactions do not occur by the biomolecular mechanism discussed above. Instead, these occur by an entirely different mechanism called the benzene mechanism or elimination addition mechanism. This mechanism involves two steps. First, elimination and second, addition. First, in the elimination step, the amide ion abstracts a proton to form a carbon ion which then loses the halide to form the benzene. Second, in the addition step, the nucleophilic attack by the amide ion occurs on the benzene intermediates, forming a carbon ion, which in turn abstracts a proton from ammonia to yield the substituted product. Evidence in support of benzene mechanism. The mechanism is supported by the following experimental facts. First, aryl halides which do not have a hydrogen ortho to the halogen atom do not react under similar conditions. For example, 2-bromo-3-methyl anisole does not react at all since the benzene intermediate cannot be formed due to absence of hydrogen atoms at ortho positions with respect to bromine. Second, isotope effect. Ortho uh, Deotriobromobenzene reacts at a slower rate than bromobenzene. This is due to the reason that a carbon and D bond is more difficult to break than a carbon hydrogen bond. This isotope effect suggests that orthohydrogen with respect to the halogen is involved in the rate determining step during the elimination stage. Third, traces studies. When labeled chlorobenzene, in which chlorine is attached to carbon isotope marked as carbon, is treated with NaNH2 in liquid, NH3, two a type of anilines are formed, one in which the NH2 was linked to carbon labeled carbon, while the other in which the NH2 group was present on a carbon ortho to the labeled carbon as shown below. This experimental fact can be explained only if we assume that the reaction occurs through a benzene intermediate. In the benzene thus formed, the labeled carbon and the one next to it are equivalent. As a result, the effect by NH2 on these two triply bonded carbon atoms occurs with almost equal, except for small isotope effect, probability giving two types of anilines. Fourth, same product from different aryl halides. When meta-bromoanisole and ortho-bromoanisole were treated separately with NaNH2 in liquid NH3, the same product, that is meta-anisidine, was formed in each case. The formation of the same product is due to the formation of the same benzene intermediate as shown below. Fifth, formation meta and para products from the para substituted alkyl halides. When para-chlorotoluene is treated with NaNH2 and liquid NH3, a mixture of meta and para-toluenes is obtained in which meta isomer predominates. This can be explained only in terms of benzene intermediate mechanism as depicted below. Heading 9.14, Relative reactivities of alkyl halides versus allyl, vinyl and aryl halides. We have discussed above that alkyl halides are more reactive than vinyl and aryl halides towards nucleophilic substitution reaction. Like alkyl halides, the halogen atom in allyl halides is also attached to the sp3 hybridized carbon. Therefore, allyl halides should be at least as reactive as alkyl halides. Actually, it has been found that allyl halides are even more reactive than 1-degree alkyl halides, with the only difference that whereas 1-degree alkyl halides always react by SN2 mechanism, allyl halides react both by SN1 and SN2 mechanism. This may be explained as follows. First, reactivity in SN1 reaction. We have discussed above that SN1 reaction occurs through a carbocation intermediate. Evidently, the more stable the carbocation intermediate, faster is the SN1 reaction. Now, since the heterolytic bond dissociation energy of allyl chloride is 724 kJ per mole, which is about 50 kJ per mole less than that of N-propyl chloride and about the same as that of isopropyl chloride 711 kJ per mole. Therefore, allyl carbocation, although 1 degree in nature, is almost as stable as 2 degree alkyl carbocation. Thus, allyl halides are more reactive than 1 degree alkyl halides, or are almost as reactive as 2 degree alkyl halides because they are readily ionized to give high resonance stabilized allyl carbocation. An interesting feature of allyl halides is that their nucleophilic substitution reaction are often accompanied by rearrangements. This is due to the reason that the allyl carbocation can be attacked by the nucleophile at either of the two allylic positions, giving rise to two products which differ only in the position of the substituent. With simple allyl halides, the nucleophilic substitution would yield the same product because the two allylic sites are chemically equivalent. However, with substituted allylic compound, two different products are formed since the two sides of the allylic carbocation are no longer chemically equivalent. The reaction in which the nucleophile gets attached to that carbon from which the leaving group has departed is called the usual NS1 reaction, whereas that in which the nucleophile gets attached to the other carbon atom is called SN1 substitution nucleophilic unimolecular with rearrangement. Now, if allyl cation is produced as an intermediate, the two products would be obtained in the same ratio no matter which of the two isomeric allylic substrates are used. This has actually been found to be true. For example, two isomeric allyl chlorides first and second yield a mixture of two isomeric alcohols third and fourth in the same ratio, no matter whether chloride first or second has been used. Second, reactivity in SN2 reactions. In SN2 reactions, carbocation intermediates are not formed and the reactivity of alkyl halides mainly depends on the steric factors. Since the allyl group has approximately the same size as that of unsubstituted 1 degree alkyl halide, therefore both allyl halide and 1 degree alkyl halide do not provide any steric hindrance to the attack of the nucleophile. In other words, the relative reactivities of unsubstituted 1 degree alkyl halides and allyl halides are almost comparable. An example of SN2 substitution nucleophilic bimolecular with rearrangement is provided by the reaction of 3-chloro-1-pentene with carbanion derived from diethyl malonate. Heading 9.15 Relative reactivities of nuclear and side chain substituted halogen derivatives. The side chain halogen derivatives, that is arylkyl halides, are much more reactive than nuclear halogen derivatives, that is aryl halides. This may be explained as follows. First, resonance effect. In case of aryl halides, the lone pair of electrons on the halogen atom are in conjugation with the pi electrons of the benzene or the aryl group. As a result, resonance occurs and the carbon X bond acquires some double bond character and hence cannot be easily displaced. In case of alkyl halides, the pi electrons of the benzene ring are separated from the lone pair of electrons on the halogen atom by sp3 hybridized carbon. As a result, resonance cannot occur and hence the carbon X bond, like in alkyl halides, has only single bond character in other words, carbon X bond is alkyl halides is weaker than carbon X bond in aryl halides and hence can be more easily broken. Further, due to weaker carbon X bond, alkyl halides readily undergo ionization to form benzyl carbocation, which is stabilized by resonance. Since benzyl carbocation is a reactive chemical species, therefore it readily undergoes nucleophilic substitution reaction. Second, on the basis of hybridization of carbon. In aryl halides, that is in carbon chlorobenzene, the carbon atom carrying the chlorine atom is sp2 hybridized, while in alkyl halides, that is benzyl chloride, it is sp3 hybridized. Since a sp2 hybridized orbital is smaller in size than sp3 hybridized orbital, therefore carbon chlorine bond in benzyl chloride is longer than in chlorobenzene and hence can be easily broken. Thus, in the light of above discussed ion, we conclude that benzyl chloride is much more reactive than chlorobenzene because of weaker carbon chlorine bond and resonance stabilization of benzyl carbocation formed after cleavage of this bond. Heading 9.16 Chemical properties of aryl halides. Some important reactions of haloarenes are given below. First, nucleophilic substitution reaction. We have discussed above that the halogen atom attached to the benzene ring is firmly held and hence cannot be easily displaced by nucleophiles such as OH negative, CN negative, etc. In other words, haloarenes are much less reactive than haloalkanes towards nucleophilic substitution reaction. However, under drastic conditions, they do undergo nucleophilic substitution reaction as shown below. First, reaction with sodium hydroxide. When heated with an aqueous solution of NaOH at 623 Kelvin and under a pressure of 300 atmospheres, haloarenes form sodium phenoxides which upon acidification give phenols. This reaction forms the basis of Dow process for the manufacture of phenol. This reaction is believed to occur all through benzene intermediate as shown below. This mechanism is supported by the observation that diphenyl ether and paraphenyl phenol are the byproducts of this reaction. Second, reaction with ammonia. When haloarenes are heated with aqueous NH3 solution in presence of cuprous oxide as catalyst at 475 Kelvin and under a pressure of 60 atmospheres, the halogen is replaced by the amino group. This reaction also occurs by benzene mechanism. Second, electrophilic substitution reaction. Haloarenes undergo the usual electrophilic substitution reaction of the benzene ring such as halogenation, nitration, sulfonation and Friedel-Crafts reaction. Halogen atom is slightly deactivating and ortho-para directing. Therefore, further the substitution occurs at ortho and para position with respect to the halogen atom. The ortho-para directing influence of the halogen atom can be easily understood if we consider the resonance structure of chlorobenzene as given on page 462. In structure 3rd, 4th and 5th, there is a negative charge at ortho and para position. In other words, because of resonance, the electron density increases more at ortho and para position than at meta positions. Therefore, further electrophilic substitution in haloarenes occurs at ortho and para positions. However, because of steric hindrance at the ortho position, para product usually predominates over the ortho product. Further, the halogen atom, because of its minus I effect, has some tendency to withdraw electron from the benzene ring. As a result, the ring gets somewhat deactivated as compared to benzene, and hence the further electrophilic substitution reaction in haloarenes occurs slowly and under more drastic condition as compared to those in benzene. First, halogenation. Second, nitration. Third, sulfonation. Fourth, Friedel-Crafts reaction. Third, reaction with cuprous cyanide. When heated with cuprous cyanide at 475 Kelvin in presence of pyridine or dimethylformamide DMF, the bromine atom of the aryl bromide is replaced by the CN group. Benzonitrile can be converted into many other useful compounds. Third, miscellaneous reactions. Beside these nucleophilic and electrophilic substitution reaction, haloarenes undergo a number of other reactions as discussed below. First, reaction with sodium. A. Wurtz fitting reaction. Haloarenes, when treated with an ethereal solution of an alkyl halide in presence of sodium, form alkyl derivative of benzene. This reaction is called Wurtz fitting reaction. B. Fitting reaction. When only haloarenes are treated with sodium diaryls are produced, this reaction is called fitting reaction. Second, reaction with copper powder, Ullmann by Aryl synthesis. When an iodoarene is heated with copper powder in a sealed tube, diaryl is formed. This is called Ullmann by Aryl synthesis. Aryl chlorides and bromides do not react unless an electron withdrawing group is present at ortho and para position with respect to the halogen atom. Third, reaction with magnesium. Bromo and iodoarenes from Grignard reagent, when their ethereal solution is treated with magnesium turnings. Chloroarenes from Grignard reagent only if the reaction is carried out in dry tetrahydrofuran THF as solvent. Fourth, reaction with lithium. Bromo and iodoarenes also react with lithium metal in presence of dry ether to form corresponding organometallic compounds. Fifth, reduction. Haloarenes can be converted into the corresponding arenes by reduction with nickel aluminium alloy in presence of alkali. Heading 9.17. Chemical properties of side chain substituted halogen derivatives. Both in side chain substituted halogen derivatives, that is alkyl halides and alkyl halides, the halogen is attached to sp3 hybridized carbon atom and hence are as reactive as alkyl halides. However, if the halogen is present at the benzylic carbon, that is benzyl halides, then these halides are even more reactive since they readily undergo ionization to form resonance stabilized benzyl carbocation. Some important chemical reactions of benzyl halides are discussed below. First, reaction with alkalis. Side chain substituted halogen derivatives are readily hydrolyzed in aqueous solution. This hydrolysis to benzaldehyde can also be carried out in aqueous acids. Second, halogenation of the side chain. When Cl2 is passed through boiling benzyl chloride in presence of sunlight, side chain halogenation occurs. Third, reaction with alcoholic ammonia. Fourth, reaction with KCN and AgCN. Benzyl cyanide can be reduced to beta-phenyl ethylamine or hydrolyzed to phenyl acetic acid. Fifth, reaction with magnesium. Benzyl chloride reacts with magnesium in dry ether to form Grignard reagent. Sixth, Friedel-Crafts reaction. Benzyl chloride reacts with benzene in presence of anhydrous AlCl3 to form higher arenes. Seventh, Wurtz reaction. When heated with sodium in dry ether, two molecules of benzyl chloride react to form 1,2-diphenylethane. With alkyl halides, higher alkyl benzenes are obtained. Eighth, reduction. Reduction with zinc and Cu couple and alcohol gives toluene. Ninth, oxidation. On boiling with aqueous lead nitrate in a current of CO2, it gives benzaldehyde. With strong oxidizing agents such as concentrated HNO3, KMNO4, KOH, or K2Cr2O7 and H2SO4, etc., benzoic acid is obtained. 10th, electrophilic substitution reaction of the benzene ring. Benzyl chloride undergoes halogenation, nitration, and sulfonation to give a mixture of corresponding ortho and para products. Heading 9.18 DDT, that is 2,2-bis 4-chlorophenyl 1,1,1 trichloroethene. General, DDT stands for para-dichloro-diphenyl trichloroethene. In fact, this name is misnomer. Its actual name is 2,2-bis 4-chlorophenyl 1,1,1 trichloroethene. Preparation. It is prepared by heating chlorobenzene with chloral trichloroacetaldehyde in presence of concentrated H2SO4. Uses. DDT is a cheap but powerful insecticide. It is widely used for sugarcane and fodder crops and to kill mosquitoes and other insects. It is particularly very effective against Anopheles mosquitoes which spread malaria. Through its use, malaria has virtually been eliminated from India and large part of the world. Tragic side effects. DDT is not biodegradable. Its residues accumulate in environment which are toxic to mammals and human beings. Therefore, its use has been abandoned in many Western countries. However, in India, in spite of these tragic side effects, DDT is still being widely used due to the non-availability of any other cheaper insecticide. Heading 9.19 Benzene hexachloride BHC C6H6Cl6. The trade name of benzene hexachloride is Gramexane or Lindane or 666. Its IUPAC name is 1,2,3,4,5,6 hexachlorocyclohexane. Preparation. It is prepared commercially by chlorination of benzene in presence of ultraviolet light. It occurs in a number of stereoisomeric forms, but the gamma isomer is the most effective. Uses. It is extensively used as a pesticide in agriculture for exterminating, killing termite white ants from soil. Heading 9.20 Furans. Chlorofluoro compounds of methane and ethene are collectively called furans. These are further classified on the basis of number of fluorine atoms present in them. For example, CF4, furan 14, CF3Cl, furan 13, CF2Cl2, furan 12, CFCl3, furan 11. Out of all these furans, furan 12 is the most widely used refrigerant. It is manufactured from carbon tetrachloride by Schwarz reaction. It may also be prepared by passing HF through CCl4 in presence of antimony trichloride as catalyst. Furan is an odorless, non-corrosive, non-toxic gas which is stable even at high temperatures and pressures. It has low boiling point, low specific heat, and can be easily liquefied by applying pressure at room temperature. It is therefore widely used as a refrigerant, cooling agent in refrigerators and air conditioners. It is also used as a propellant in aerosols and forms, that is, air sprays, deodorants, shaving creams, cleansers, insecticides, etc. Recently, it has been shown that phenol is responsible for destruction of the ozone layer in the upper atmosphere. Therefore, its use as propellants in aerosols has been banned in USA. This was all about alkyl and aryl halides.